Good day, everyone. We're reviewing Wetzel's Limnology textbook. This is edition number 4, and we're on chapter 12, which looks at salinity and ion composition of inland waters. And today we'll be looking at starting with anthropogenic sources of salinity. The exploitation of geological resources for human use, agricultural intensification, industrialization, and urbanization all contribute to changing ion contributions to surface waters. Point source pollutants include but are not limited to industrial outflows, wastewater effluents, and mining waste. A notable point source pollutant that quickly became globally pervasive was the industrial emission of sulfur and nitrogen compounds, namely from the burning of fossil fuels by power plants. Sulfuric and nitric acids in the atmosphere led to the widespread acidification of aquatic ecosystems, particularly in northeastern North America and Scandinavia. The devastation of acid rain on the chemistry of surface waters in the 1960s through the 1980s led to global action to curtail its effects. In extreme cases, lakes were lined with calcium carbonate to buffer the acidification. Coordinated policy actions by multiple countries have drastically curtailed acid rain, and 50 years later, it is looked upon as an environmental policy success. And many lakes have recovered or are well on their way to recovery. However, aquatic ecosystems are still at risk of atmospheric pollutants, especially in industrializing countries such as China and India. Non-point source pollutants of major ions are equally prevalent. Common agricultural fertilizers include potash, calcium, which is potassium chloride, and sulfur additions. The addition of ammonium fertilizer has also been found to mobilize base cations via soil acidification. Livestock manure applied to cultivated land can similarly contribute ions. In many cold regions, road de-icing, sodium chloride, calcium chloride, magnesium chloride, applied to impervious surfaces have resulted in increasing chloride concentrations in numerous lakes, and they are the leading cause of salinization in many regions of the United States and Canada. In the United States, over 20 million tons are applied to U.S. roadways annually. All of this salt ends up in terrestrial and aquatic environments. In addition, urbanization has increased anions, cations, and silica loading to surface waters through both direct sources such as concrete weathering and sewage leakage, and indirect feedback from land use change and elevated urban temperatures. Humans are altering natural salt concentration in inland waters not only through changing in ion contribution but through the diversion and withdrawal of freshwater flows. Where lake inflow is reduced, the shift in water balance leads to ion concentration via evaporation. This salinization threat is compounded by human-induced climate change, environmental influences on salinity. Climate affects the balance between precipitation and evaporation, and thus the salinity of surface waters. In closed drainage basins, the salinity of lake waters is governed not only by inputs of dissolved ions from runoff, but by the fate of these materials upon evaporation. As water evaporates from a lake basin, ions become concentrated and salinity increases. Most closed basin lakes, termed endorheic lakes, occur in regions with long-term, several years, fluctuating climates and are often exposed to periods of severe aridity. If shallow, these lakes may evaporate completely or sufficiently to expose large expanses of sediments. Diversions of river inputs by human activities, as in the tragedy of the Aral Sea, can also lead to the exposure of large areas of sediments. Loss of dried salt then occurs via wind deflation, the removal of loose, small surface material by wind. So before we move on, let's look at figure 12-6. A is chloride trends for North American freshwater lakes in areas of heavy road salt applications. Points are colored by the slope value of linear regression models: red positive, yellow negative, purple yellow negative slope, and purple zero or non-significant slope. Squares denote lakes with at least biannual chloride concentration recorded from 1985 to 2010 with a sample size of 52. So here we have the squares and we have decadal records, and then here we have the circles, and we have also records over the time period of 1985 to 2010. So this is 214 lakes versus 52 lakes. All in all, what we can see here is that a lot of the lakes in the northeastern part of the U.S. as well as the upper part of the Midwest are impacted by salinity, because we have a lot of red dots or red squares. And then here we have the author that is standing in a salt storage shed with a huge salt pile behind her. Other significant climatic factors influencing salinity are temperature, wind, and ice formation. Temperature influences the rate of rock weathering. Tropical waters, for example, which drain strongly weathered soils, are usually poor in electrolytes, and a large part of their total composition consists of silica. The type of vegetation growing on the drainage basin and its requirements for major ions are also influenced by climate. Mineral cycling in tropical perennial forests of dense vegetative cover, for example, differs greatly in higher rates of utilization and leaching of soil nutrients as compared to nutrient cycling in deciduous vegetation of temperate regions. Wind direction and speed may affect the chemical composition of atmospheric precipitation by altering the amount of incorporated sea salinity and sites of deposition inland. Lastly, for lakes and rivers that experience winter ice cover, ion rejection during ice formation will increase ion concentration in the water column. These can temporarily and significantly increase ion concentration in shallow water bodies. The magnitude and variability of environmental influences on inland water salinity are predicted to increase in the future due to climate change. Regionally, the effects of climate change will differ. In coastal areas, sea level rise threatens freshwater habitats through seawater intrusion and the salinization of groundwater. As the Earth's surface warms, evaporation of surface water will increase. The concentrating effect of evaporation may be offset by increasing precipitation or exacerbated by increased aridity and the occurrence of drought. Overall, it is expected that increased evaporation and a decrease in precipitation driven by climate change pose a salinization risk for many inland water bodies. Even saline lakes in historically arid regions are at risk of desiccation in the wake of climate change. Saline lakes. Saline lakes are found on every continent on Earth. Athalasic means not to the sea, was a term originally intended to differentiate inland waters with ions derived from terrestrial and atmospheric sources from those of marine origin, such as the Caspian Sea. While the definition does not provide a salinity threshold, and therefore all freshwater lakes are by nature athalasic. The term athalasic is typically reserved for saline lakes. Non-marine influenced saline lakes form and persist when outflow of water is restricted, as in hydrologically closed basin. Evaporation exceeds inflow, and the inflow is sufficient to sustain a standing body of water. Saline lakes display a range of brine composition that are a result of the interplay of hydrology, evaporation, and geology. Ionic composition often evolves towards sodium-rich brines due to the precipitation of alkaline earth minerals. Such lakes include Great Salt Lake and Mono Lake, and Lake Erie in Australia. Calcium-rich brines do exist where groundwater catchments inputs dominate over evaporative processes. Don Juan Pond in Antarctica, for example. Chloride very commonly predominates due to the precipitation of carbonate and sulfate minerals. Certain elements normally present in only trace amounts in surface waters can occur in very high concentration in saline lakes, which has led to the economic use of salt lakes as a source of minerals. The salinities of the world's saline lakes are often in flux due to the tight coupling of ion concentration with climates. In addition to being hydrologically and chemically fascinating, saline lakes are also biologically peculiar and host important biodiversity among their highly specialized biota. So before we move on, let's look at this figure here. Figure 12-7, global diversity of saline lakes. So A is Mono Lake, B is Lake Korangamite in Australia, C is Lake Ormia in Iran, D is Lake Bogoria in Kenya. E is Lake Bonny and Blood Falls in Antarctica. So I believe this is the lake and this is the Blood Falls. This is the Great Salt Lake in Utah. G is Shaka Salt Lake in Qinghai, China. And then H is the Don Juan Pond in the Wright Valley of Antarctica. So I think the pond is right here. So from the get-go, what we can see is that we have a lot of different type of saline lakes in a lot of different types of environment, running from Antarctica all the way to tropical / nearly equatorial region, like in Kenya right here, as well as including, of course, arid areas such as this lake in Iran. Distribution of major ions in fresh waters. All major ions are essential to sustaining life in inland waters. The spatial and temporal distribution of the major cations and anions are separable into conservative ions, whose concentration within a lake and many streams undergo relatively minor changes from biological and geochemical processes, and 2, non-conservative or dynamic ions, whose concentration can be influenced strongly by biological and geochemical processes. Of the major cations, magnesium, sodium, and potassium ions are relatively conservative, both in their chemical reactivity under typical freshwater conditions and their small biotic requirements. Calcium is more reactive and can exhibit marked seasonal and spatial dynamics. Of major anions, inorganic carbon is so fundamental to the metabolism of freshwaters that it is treated in a separate chapter and later coupled with organic carbon cycling. Similarly, sulfate is greatly influenced by microbial cycling and the chemical milieu and is treated separately along with iron and silica. Chloride is highly conservative. The total ionic salinity, composed almost entirely of the 8 major ions, calcium, magnesium, sodium, potassium, bicarbonate, carbonate, sulfate, and chloride, is of the major importance in the osmotic regulations of metabolism and in the distribution of biota. The biological importance of these ions is briefly discussed below and in chapter 13 and 14 and 16. So 13 for bicarbonate and carbonate and 16 for sulfate. Calcium. Calcium influences the growth and population dynamics of freshwater flora and fauna, both directly and indirectly. Plants require calcium for development, regulatory processes, and signal transduction, and it is also a fundamental component of the oxygen evolving complex in photosystem 2 in phytoplankton, including cyanobacteria. In animals, calcium is an essential mineral. It is needed for bone and exoskeleton formation and molecular signaling, and can limit growth and development at low concentrations. Some organisms require high calcium concentration, and low concentration can limit their distribution. For example, certain species of the zooplankton Cladocera daphnia, which is a dominant keystone grazer in many temperate freshwater lakes, has a calcium-rich chitinous exoskeleton. When calcium concentrations are less than 2 milligrams per liter, the fitness of certain large daphnia species decreases. In some Canadian lakes, a decline in calcium has resulted in daphnia being replaced by Holopedium glacialis, a Cladocera, with 1/10 the calcium requirements of daphnia. Similarly, crayfish require calcium for their exoskeleton, and mussels require calcium for their shells. Low calcium concentration may protect lakes from the spread of invasive species such as rusty crayfish, with a calcium of less than 2.5 milligrams per liter, and zebra and quagga mussels with calcium less than 12 milligrams per liter. Many inland waters have calcium concentration close to this threshold. A global analysis of rivers and lakes found median calcium concentration of 3.76 and 5.50 milligrams per liter, respectively. The lowest calcium concentration were found in boreal regions of Fennoscandia and Canada, and some tropical regions of South America. Dissolved calcium is removed from the water column, both biogenically from the formation of calcareous skeleton and other organism structures, and through biogenic and inorganic precipitation of carbon minerals. Whiting events are striking phenomena where calcium carbonate precipitate in the water column, turning lakes a chalky white color. Whiting events are known to be triggered by large phytoplankton blooms that rapidly raise the pH of surface waters, thereby decreasing calcite solubility. As discussed previously, the major source of calcium in inland waters is rock weathering of calcium carbonate and calcium silicate, and input rates should be relatively constant. However, when acidified from acid rain, terrestrial landscape leach cations through cation exchange displacement by hydrogen and aluminum ions in soils. Through this process, calcium and magnesium concentration are depleted in soils and increase in surface runoff. As rivers and lakes recover from acidification, one consequence is a long-term decline in calcium concentration, even to concentration below pre-acidification concentrations, due to the depletion of cations in catchment soils. Globally, many lakes affected by acid rain are currently in the recovery phase. Before we move on, let's look at this figure here, figure 12-8, that looks like at the global distribution of long-term median calcium concentration in milligrams per liter in lakes and running waters. And so we have the insets for South Africa, which is right here, Europe, and Japan. So let's first look at just globally what's going on. So a lot of our concentration when it's dark are greater than 5, or at least 5 and up to 20 milligrams per liter. So we can see that it's the case in North America, although not really like in the Cascades or in the Pacific Northwest. We have concentration between 5 and 20. Then in Europe, so Europe, if we look at the inset, we have like Fennoscandia, which is basically pretty much Scandinavia with Finland included. We have quite a variable amount of concentration. Like Western Norway, for example, has pretty low calcium concentration, but Southern Sweden has higher concentrations, as well as Eastern Sweden here. Finland itself, it's in kind of in the average range. And then as you move north, the calcium concentration seems to decrease. Japan has a pretty even concentration of calcium throughout the islands. There's not much difference, so it ranges between 5 and 20. And South Africa, here, which is kind of really dark, which you would assume that is greater than 20, it's not necessarily always the case. So you have like pretty high concentration, like in the northeastern part of South Africa, near Lesotho, but then like in the southwestern part near Cape Town and the likes, the concentration are getting into the average range. The calcium content of soft water lakes and streams remains well below saturation levels, and these concentrations exhibit minor seasonal variation with depth. The amount of calcium used by the biota is usually so small in comparison to existing concentrations that reduction or depletion by biota cannot be seen in normal analysis. Decomposition processes can lead to some calcium accumulation in the hypolimnion of productive saltwater lakes during stratification. The calcium content of hard water lakes, however, undergoes marked seasonal dynamics. The changes depicted in figure 12-9b for a hard water lake in southern Wisconsin are quite typical. Between rather uniform concentration during spring and fall periods of mixing, a conspicuous stratification occurs that is repeated annually with only minor variations. The concentration of calcium decreased markedly in the epilimnion as a result of precipitation of calcium carbonate during the summer months from May through September. Similar losses are known to take place during the period of winter stratification. In winter, decreases beneath lake ice are associated in part with dilution by rains permeating the ice and melting ice, as well as with increases in photosynthesis just before ice loss. Decreases in the concentration of calcium and of inorganic carbon in the epilimnion and metalimnion are related largely to rapid increases in the rates of photosynthesis by the phytoplankton and littoral flora, and indicate the major role of photosynthetic alteration of carbonate equilibria and induction of epilimnitic decalcification. The loss of calcium carbonate influences the metabolism of hard water lakes via the co-precipitation of inorganic nutrients such as phosphorus and selective removal of humic organic acids and other organic compounds by adsorptions. So I think we're going to be leaving it here today, and we'll pick it up tomorrow with this review of this figure 12-9, as well as the epilimnetic declassification topic right here. So thank you for your attendance, and I'll see you tomorrow. Bye.